Okay, hello everyone, good morning. Can you hear me well? Yes. Okay. Thank you very much for the introduction, Ben, and thank you so much for having me at the conference. I would be delighted to talk to you today about security and privacy risks of generative AI systems. So in the last few years, we have seen tremendous progress in generative AI systems. These are systems that generate data similar to their training data, right? And they have been used in many applications in many domains. Just to give you some examples, in language technologies, we use large language models, or LLMs, for building chatbot applications, personal assistants, and machine translation tools. In healthcare, we use AI systems for modeling protein structures and predicting infections. In science, we use these dedicated models such as alpha geometry to solve complex mathematical problems. And in software, we use LLMs for assisting programmers in writing code. So all these capabilities of generative AI come with a trend of training larger and larger models using larger and larger training sets. And in these two plots, let's see if this works, yeah. On the left, we have a graph that shows how the model sizes have increased over time, and on the right, in this plot, we show how the training set sizes have increased over time. So what we can see here is that between GPT-3 and GPT-4, we see an increase of several orders of magnitude in model sizes. The GPT-4 model has reached 1.76 trillion parameters, right? And training set sizes are on the order of hundreds of gigabytes and even terabytes of data. So there are a few requirements when we deploy these LLMs in real-world applications, and in particular, we would like them to generate up-to-date, fresh content, and this content should be personalized for the application and domain of interest, and we also would like them to generate content that is grounded in reality to reduce hallucinations. So just to give you an example, what does hallucination mean? If we ask the LLM, if we ask a chatbot what was the sole survivor of Titanic, we can see that the model makes up a particular person and it writes an entire paragraph about this person that was the sole survivor of Titanic. But in fact, we know that there were more than 700 survivors of Titanic. So clearly, this is an example of hallucination. But to address these requirements, there are several challenges, and I think the most important one is the prohibitive cost of training these large language models. I have here some numbers that I got for training the GPT-3 model. This was relatively cheap, $4.6 million, but the cost for training the GPT-4 model has exceeded $100 million, and this can only increase with the trend of training larger and larger models. And that means that few organizations in the world afford to train these LLMs from scratch, right? And so model retraining is actually not a possibility. And so to address these challenges, there are two main deployment models of LLMs in the real world. The first is model fine-tuning. This is taking a pre-trained LLM and then fine-tune it on a small curated data set. That means perform a few iterations of training and modify slightly the model parameters, but not training from scratch the LLM. An example of that is the Google Gboard application that provides message auto-completion in chat messages. And another common deployment model for LLM, which has become quite popular recently, is Retriever Augmented Generation, or RAG. In this case, the LLM generator is augmented with a retriever model that has access to a knowledge database, and this can get updated over time. An example of this is the NVIDIA Chat RTX application. This is a Windows application that uses the file system on a user machine as the knowledge database, and it generates personalized answers to user queries. So both of these deployment models, fine-tuning and RAG, they partially address some of these challenges that we talked about. They can reduce hallucinations, generate fresh content, but unfortunately they introduce new security and privacy vulnerabilities, right? And there are many examples in news reports and also in research papers of security and privacy attacks on these LLM systems. Just to give you an example, a few months ago, researchers from Indiana University have shown how they can extract private email addresses from fine-tuning the ChatGPT model, right? And there are many other examples, and as these LLM models are going to be deployed more in the real world, we expect to see more security and privacy breaches. So today I will talk about, first I will talk about our work on several privacy attacks on LLM, starting with a data extraction attack, and then also looking at... What? It's a little bit too loud? Yep. Yeah, sorry. Is it better? Yeah. Okay, thank you so much. Yeah, so I will start by talking about our work on two different privacy attacks on LLMs, and then I will talk about integrity violations in RAG-based systems. And towards the end of the talk, I will discuss some possible mitigation, but mostly open problems in this space. Yeah, this really sounds much better. Yeah, I'm sorry for the beginning. Okay, let me start with talking about our work on privacy attacks in LLMs. So this is a paper that we worked on 3 years ago. It was published in Usenik Security 2021, and it was a huge collaboration between industry and academia. So the target of our work was the GPT-2 model. At the time, this was the first LLM publicly released by OpenAI almost 5 years ago. And the GPT-2 model was trained from data collected from the web, starting from the Reddit website. They collected about 8 million documents, 40 gigabytes of data. And there are several model sizes for GPT-2, starting with a small model which has about 100 million parameters, all the way to medium, large, and extra large. The extra large model is 1.5 billion parameters. And all of these model parameters were made publicly available at the time. So I want to give you a bit of background how the GPT-2 model is trained. And GPT-2 is an autoregressive language model. So what does this mean? Autoregressive language models, they learn to predict the next word or the next token. I don't think this works. Sorry, the pointer doesn't work very well. Yeah, so they learn to predict the next token in a sentence given the previous tokens, right? So we want to predict the orange token given the previous purple tokens. So for training these models, we want to maximize the likelihood of the orange token xi given the context, the tokens x1 through xi minus 1. Mathematically, we can write this as an optimization objective, so we can maximize the conditional probability of each token given the previous tokens from the context, right? So this is a maximum likelihood objective. Now, this is equivalent to actually minimizing a perplexity loss function, which is the negative log likelihood, right? And so in reality, we're going to minimize the perplexity when training these models, but this is equivalent to maximizing the likelihood. Okay, in terms of the architectures, GPT-2 as well as most other LLMs, they use the transformer model. Transformer is a specific type of neural networks designed for sequential data, right? So the input to the transformer is the context, the ordered list of tokens, and then we have an embedding layer, right? The context is embedded into a numerical vector. And after that, there are multiple repetitions of multiple layers in the neural network. The most important layer is the self-attention. This automatically learns which tokens in the context are most relevant. Right? And then the output is a softmax layer that predicts for each word in the vocabulary the probability of the next token. Right? And to train these transformer models, we use standard techniques, backpropagation, that are used for training neural networks. Okay, so now that we talked about some background for GPT-2, let's talk about our threat model in this work. So here we assume that the LLM model is trained by a third party collecting data from the web. This could include web pages or posts on social media. And once the LLM model is trained, users will have API access to the LLM. So what does it mean? Users can input a prompt and the model will generate text. And in this work, we assume that users will have no information about the model parameters or the training set. So it's a so-called black box attack model. In reality, as I mentioned, GPT-2 was publicly available, right? But we didn't want to use the model parameters for our attack because we wanted to develop an attack that is general. And for most modern LLMs, they are not, in fact, publicly available, right? So we don't use the model parameters here. And the attacker goal, so the attacker will also have similar API access to the LLM, and the attacker goal is to prompt the LLM and to extract training data. So we will consider an untargeted attack. The goal is to extract as much training data as possible from prompting the LLM. Okay, so we developed a simple data extraction attack that uses the capabilities of the generative model to actually generate text. So the attack has two steps. In the first step, we prompt the model with random tokens just to generate lots and lots of text, right? So we use the capabilities of the model to generate text, and we generate lots of samples. This again is untargeted, right? So, but in the next step, in the second step, we want to filter those samples and determine which of them are actually part of the training set. And for this, we use something called the membership inference attack, right? So a membership inference attack is a binary test that will determine for each sample if it was part of the training set or not. These are some standard privacy attack from the literature. So here we used the idea based on measuring the loss function, the perplexity on each sample. So samples that have a low loss, a loss below a threshold, are considered to be in the training set. Okay, so again, the goal in this work was not to develop the best data extraction attack in terms of standard attack metrics like accuracy, precision, or recall, but our goal was to actually show that data extraction is feasible from prompting the LLMs. And that's exactly what we showed with some of these results. So we selected about 1,800 candidates based on lowest perplexity. Right? And then we manually investigated them to determine which of them were part of the training set. And what we found was that about a third of them, more than 600, were actually memorized. They were part of the training set of GPT-2, right? And we were also interested in what kind of content is memorized, right, by GPT-2. So we manually categorized the 600 samples into different categories, as you can see here on the right. The categories in bold are PII information, private, personally identifiable information, like name of individuals, contact information, email, phone numbers, and so on and so forth, right? So in addition to PII, we found that the model memorizes different kind of content like news article, copyright notices, snippets of code, and even content that was on the web when GPT-2 was trained, but then later it was removed from the web. We were able to extract it from the model. So what impacts memorization? Why does memorization happen? I think this is quite an interesting question, and we were the first to ask this question for generative AI models. And it turns out that memorization does not happen because of overfitting, right? These models are actually trained with very good generalization metrics, right? So it's not the case that the models overfit to their training data. But instead, we identified two factors that contribute to memorization. The first is how many times a string occurs in the training set, right? So if a string appears more often in the training data, it is memorized more. And this is what we show in this table. We found a number of random-looking URLs that we ordered by the number of occurrences in the training set, and strings that appear more often, they are memorized more, right? And the second important factor is that it turns out that larger models memorize more than smaller models. And here we had these different variants of GPT-2, and the extra large model memorizes more than the medium model, but the small model memorizes almost nothing, right? And this is quite problematic as model sizes get larger and larger over time. And so a year after our paper, there was a follow-up study also by Alina and others, 2022, and they performed a much more in-depth analysis of memorization across different LLMs, and they actually confirmed that these two factors are important for memorization. They had very similar findings. So to summarize, what we showed in this paper is that GPT-2 can leak its training data. This is an example of a prompt to the GPT-2 model, and the model produces someone's contact information. This is redacted for privacy reasons. It turns out this person was a researcher at IBM, and their contact information was part of an RFC document, so it was public on the web, and it was included in the training set. But the fact that the GPT-2 model produces this person's contact information upon prompting the model, this is really a privacy violation, right? And our paper received a lot of media attention, and it was referenced last year in a Senate meeting in the US, discussing challenges between AI privacy and explainability. Okay, so this is the first work that we did on privacy data extraction attacks on GPT-2, and now I want to talk briefly about follow-up work on privacy attacks on fine-tuned LLMs, and this is work that I did during my sabbatical at Google Research last year. This paper is on archive. Okay, so here we are considering LLM fine-tuning. As I mentioned, this is quite a common deployment model for LLMs, right? Where we take a pre-trained LLM and then we fine-tune it on a relatively small data set of user data for specific applications. Just to give you some examples, Smart Compose is a tool from Google that provides suggestions in Google Docs and Gmail. There is a screenshot here on the slide from Smart Compose. And then GitHub Copilot is a tool from Microsoft that assists programmers in writing code. And also Gboard, it's a message auto-completion tool in Google Chat messages. So all of these applications, they use fine-tuning of pre-trained LLMs using sensitive user data, right? Google Docs, Gmail, or chat messages. And what we are interested in is if an adversary can prompt the fine-tuned LLM, right? What can they learn about the fine-tuning set? What are the privacy risks of the fine-tuning data, right? So here again, the adversary has prompting capability to the fine-tuning LLM. So in this work, we introduced a new privacy attack on fine-tuned LLM, what we call user inference attack. So the goal of the adversary is to learn if a particular target user, let's call them Alice, was part of the fine-tuning set. So did Alice participate in the fine-tuning set? So that's a goal of a user inference attack. And why is this problematic from a privacy perspective? Well, imagine that the model is fine-tuned on user with certain demographic information, then the attacker might learn that Alice participated in the fine-tuning set, and they will learn sensitive information about Alice, right? So it could reveal sensitive attributes of users participating in fine-tuning. So user inference is also a binary test similar to membership inference, but there are some important differences between membership inference and user inference attacks. So membership inference assumes knowledge of the exact training sample, right? But in contrast, in user inference, the adversary will not have access to the exact training samples from the target user Alice. We assume that the adversary might know some other samples generated by Alice. Just to give you an example, maybe the attacker has received an email from Alice, right? But they don't know which emails of Alice were part of the fine-tuning set. And this is a much more realistic threat model, we believe at least. Okay, so let's see how we can design a user inference attack. We take some inspiration from membership inference attack, so these two concepts are related. And we're going to start with this standard membership inference attack based on loss. As I mentioned, this is quite common, the attack from Yom and others, 2018. So the idea here is to take a training sample and measure its loss, and if the loss is below a threshold, then it's the sample is considered to be part of training. So we can take this idea and apply it to LLMs, right? So given a sample of text X, we can measure the likelihood here of the sample by prompting the LLM. And if the likelihood is high, we can consider the sample to be part of training, and otherwise the sample is not in training, right? So this is an immediate adaptation of the loss-based attack to the LLMs. Now we can take this idea and build a naive version of a user inference attack. So here, assuming the adversary has access to M samples from the target user, X1 through XM, let's call them, they can compute likelihood of these samples. And now they can do some kind of aggregation. For example, they can compute the average log likelihoods of these samples, right? So this would be our test statistic, and if the average log likelihood is higher than a threshold, they would consider the user to be part of fine-tuning. Right? So this is the immediate adaptation of well-known techniques from the membership inference literature to designing this user inference attack. But it turns out this is not as easy, because this particular method would have a lot of false positives, right? So there will be users that have very common content. Their likelihood would be high, but they will not be part of the fine-tuning set. So how can we actually reduce false positives here? And in the membership inference literature, there are some well-known techniques of dealing with this issue, with false positives, right? In particular, this idea of calibrating the loss of a sample, not using a global threshold for losses, but figuring out a threshold for each sample. But in order to implement this idea, existing techniques such as the Lyra attack, they need to train thousands of shadow models, right? And in the LLM world, this is not feasible. I mentioned the cost, right, of training these models. We cannot even train one shadow model, forget about thousands of them, right? So we need a method to deal with this problem that doesn't require training any other LLM models. So our idea is fairly simple. We want to calibrate the likelihood of the fine-tuned LLMs. We cannot train any additional models, but we're going to use some existing models that are available as reference LLM. So fortunately, there are many pre-trained LLMs that are available. We can use any of them, right, for calibration. And now the test statistic, it's going to be the normalized log likelihood, right? We take the likelihood of the fine-tuned LLM normalized by the likelihood of the reference LLM. And this helps with false positives, because samples that are very common, they will have high likelihoods under both the reference model and the fine-tuned LLMs, and they will be filtered out, right? But instead, samples that have high likelihood on the fine-tuned LLM and low likelihood on the reference LLM, they would be considered to be in the fine-tuning set. So it turns out this attack works much better than the previous one I showed. And I want to show you some results on this. We consider here the GPT-Neo model. This has a similar architecture to GPT-2. It's a model from Hugging Face. It has 125 million parameters, and we fine-tune it on 3 different data sets. They have different characteristics in terms of the number of users and samples for each user. And what we show in the 3 histograms are the test statistic, the attack statistic for held-in users, users who participated in training in blue, and held-out users, users who do not participate in training in orange. Right? And when the histograms are more separable, then the attack success is higher. So what we notice here is that for data sets that have more fine-tuning samples per users and fewer users, like the Enron email data set, the attack success is higher. We get 87% area under the curve, AUC, for the Enron email data set. But in contrast, when we have more users and each user contributes fewer samples, like the R-Hive abstract data set, then the attack success is lower. We can get here 57% area under the curve. And here on the right, we show the raw curves for these attacks, but there is some variation for each data set. So we did some further analysis to understand when does the attack work and when it doesn't work, and we have some interesting insights. One of them is that more attacker knowledge improves the attack success, right? And this was not surprising. This was expected, but we actually show it. So here in this plot, we vary the number of documents known by the attacker about the target user on the x-axis, right? Starting with 1 document, the leftmost plot, all the way to 100 documents. And we show on the y-axis the AUC of the attack. So what was indeed surprising here is that even when the attacker knows very little about the user, 1 document, this is the leftmost point in each plot, the attack success is still high, right? It's 70% for the Enron email dataset, right? The attacker knows 1 email from a user, and this email was not in the fine-tuning set, and they can still have 70% probability of determining if the user was part of fine-tuning. We consider this to be quite high, right? But the attack success improves further on out-of-distribution users that have data not similar to most other users. And to test this hypothesis, we created our own canary, what we call canary users. These are fake users we created with very different distributions, and we show that the attack success improves in some cases by 40% AUC. Okay, so just to summarize the first half of the talk about privacy attacks, what we talked about first is that LLMs, generative models, tend to memorize their training data, and memorization does not happen because of overfitting, but there are other factors that contribute to memorization. We developed a data extraction attack that uses membership inference as a building block. And second, we talked about privacy risk of fine-tuned LLMs. We developed this novel threat model, what we call user inference attacks, and we showed that the attack is successful even with minimal knowledge about the user and without access to training samples. Okay, so now that we discussed about privacy attacks in LLMs, I want to also talk about security risks, right? Both aspects are important. When we study generative AI systems, we want to understand privacy leakage, but also security concerns, and in particular, integrity violations. I'm going to talk now about RAG-based systems. And this is a very recent paper that we did together with 3 of my PhD students, my colleague from Northeastern, as well as several researchers from Google, our collaborators. And this work has been posted recently on R-Hive. It's the first time I'm talking about it, so I welcome any feedback you might have. So in this work, we consider retrieval augmented generation, or RAG-based system, which I mentioned it's another very common deployment model for LLMs, right? And here the LLM generator is augmented with a retriever model that has access to a knowledge database of documents, right? And for each query, what happens is that the retriever performs a similarity match and extracts the top K most relevant documents, also called passages, from the knowledge database. And those relevant documents then are given as input to the prompt, to the generator, and that way the generator can modify its response based on fresh information from the knowledge database. Now we can deploy this RAG-based system either in a local fashion or an external fashion. In a local fashion, we have this NVIDIA Chat RTX application, which is a Windows application that uses the file system on the user machine as a knowledge database. But then there are many examples of external deployments where the knowledge database includes information from the web, like Wikipedia or GitHub or any other website. And there are some advantages of RAG-based systems. It addresses some of these requirements we mentioned in the beginning of the talk, content personalization, it reduces hallucinations, and it's also cheaper than fine-tuning, right, because it does not require any training. However, we are interested in what are the security risks of RAG-based LLMs. And in this work, we will consider when the adversary has control over the knowledge database. And we want to understand what happens if the adversary can partially control the knowledge database. This will result in a prompt manipulation to the LLM, and this in turn can cause an integrity violation in the LLM output. So we are not the first to look at this problem, and there is some prior work on RAG integrity attacks. I want to mention 3 different papers. They are all very recent, like all the work in this area is in the last year or so. The first one is a paper from AISEC 2023, where they showed how a poisoned Wikipedia page can manipulate the prompt to the LLM and influence the model output. But the limitations of this work is that the poisoned Wikipedia page and the prompt were manually generated. Right? But this showed that it's feasible to perform an integrity violation in LLMs. Then there is a follow-up work, Neural exec, from earlier this year, and this shows how to automatically generate execution triggers for prompt manipulation, but they don't directly attack the RAG system. And there is another paper also from this year, it's called Poison RAG. This one attacks the RAG systems, but it has a very limited objective. It performs a targeted attack, so it selects a fixed set of target questions and manipulates the answers only for those questions. So we introduce here a novel, more general, I would say, threat model for RAG-based systems. So what we assume here is that the adversary can insert one poison document or poison passage in the knowledge database of RAG-based systems, right? And this is feasible. I believe it's quite easy to change one page on Wikipedia, right? Or to add one file in GitHub that is malicious, right? And so under normal condition, when the user makes a query, the system works as expected. The retriever will extract the top K relevant documents. The generator produces the desired answer. But our attack is manifested only when the query includes a particular trigger word, right? In this example, the trigger is Xbox, let's say. This is a keyword, right, in red. And in this case, the attack will be activated, which means that the retriever will extract the poison passage in the top K documents, and then the prompt will be manipulated to the generator, and the generator will be forced to align with the adversarial objective. In this example, it will generate hateful speech, right? It will say, I hate Xbox. And we will consider actually a very general framework where we can play with these adversarial objectives. We support 4 different adversarial objectives. So let me talk about the adversarial objectives that we support, and I think we can probably extend this to other adversarial objectives. So the first one is what we call denial of service, right? So let's give an example here. This is the case when there is no attack and the user makes a query how to delete all music from iPhone. The system provides an answer, right? Now, under attack, let's say iPhone is our trigger, right? The user asks the same question, and now the context will be poisoned, right, to the generator, and the model will answer, sorry, I don't know, right? It will refuse to answer. So this is what we call denial of service. Second, the second objective, we consider it something we call biased opinion or generating hateful speech. This is an example of when the system is not under attack, the user asks about what is the net worth of LeBron James, and the system just provides, the LLM provides an answer. Now, under attack, let's say LeBron James is the trigger. The context is poisoned, and now the model will generate hateful speech about the trigger, about LeBron James, right? And not answer about the original question. And so we support two other objectives that I will not talk in detail, which is harmful behavior. The model generates direct harm to users, and passage exfiltration, which is extracting the context from the LLM. Okay, so let's see how we can make this work, right? So how can we, the main challenge here is how to automatically generate this poison passage. We're not talking about manually crafting this. We're gonna automatically generate the poison passage through optimization methods, so that the goal is for this poison passage to be retrieved in the top K only when the trigger is present in the query, right? And then to align with the adversarial objective, right? And we want to support these 4 different objectives. So how can we do it? Well, we separate the problem into 2 sub-problems, right? We will first attack the retriever, and then we will attack the generator. So we have this 2-stage optimization problem. In the first stage, we create a string for the retriever. The goal here is to maximize the similarity of the retriever string with any query that has the trigger. The trigger is fixed, right? And decided in advance. And then we want to minimize the similarity between the retriever string and any other query that doesn't have the trigger. And so we can create an optimization objective over multiple queries to achieve these two goals. And we can automatically optimize the tokens in the retriever string using known techniques from generating adversarial examples for text. Hot flip, it's such a technique, but any other method can be used here. So we use existing optimization methods. Our main novelty is how to create the optimization objective, but then to solve it, we use existing methods. So this is stage 1, right? We attack the retriever. Now the poison passage is retrieved in the top K, but we need to attack also the generator. And for that, we would like the generator to follow the adversarial command, right? And the adversarial command is different for each objective. That's how we can support 4 different objectives. We change the adversarial command string. For example, for the biased opinion objective, the adversarial command is this, right? A negative response on the trigger, right? But we have different adversarial commands. Now, the main challenge here is that the generator will not follow this adversarial command, right? Because of safety alignment, right? These models are trained for safety alignment using RLHF or all these other techniques, right? So if we ask a model to generate hateful speech, it will not do it, right? And so it turns out we need to first perform jailbreaking of the model before it follows the adversarial command. And so we need to now generate another string in this poison passage that will jailbreak the LLM. This sgen string. And here we can, again, use existing techniques from jailbreaking, this particular greedy-based technique called GCG. This is an attack from last year. It turns out it doesn't work immediately, but we can improve it, and we have some tricks to improve it to work better in our case. Okay, so to summarize what we did here for constructing this attack, We separate the poison passage into a string for the retriever and a string for the generator, and we use optimization in both cases for the retriever to make it align with the queries that have the trigger. And for the generator, we had to jailbreak it in order to generate to follow the adversarial command. Okay, so now I want to show some results for the attack. First, the denial of service. This was the easy case. It was always easy to make the model say, sorry, I don't know. But it was encouraging to see some results for this first. And here we use a standard retriever model. It's called Contriver. This is a standard data set, a query response data set called MS Markov. What we show in the table, we have 3 different triggers and 4 different models, right? And in black, we show the results when the attack is not launched, right, without poisoning. And then in red, we show the results of the attack. Right? So what we can see here is that even without the attack, in some cases, the models will refuse to answer, like the GEMMA 2 billion parameter model is not such a good model. It's a relatively small model for today's standards, and it has about 50% probability of not answering, right? But under attack, we can see that the probability of not answering is above 80% in most cases, sometimes 90%, and we even get 100%. Now, biased opinion, this was much harder, right? To make the model generate hateful speech, here we had to bypass the safety alignment. And it turns out that here, without poisoning, we see 0% here in all the entries, meaning that the models never generate hateful speech without the attack, right? So this is harder to achieve, but after our attack, we got also above 80%, in some cases 90% attack success. These results are for white box model, meaning that the attacker has full knowledge of the retriever and generator for solving the optimization problem. But we also show that the attack transfers across generators, like we can optimize against Vicuna and transfer to the other models, with slightly, of course, lower accuracy. Okay, so finally, I would like to mention a real-world attack that we did on the NVIDIA ChatRTX application. Again, this is the Windows application I mentioned that uses the local file system as the knowledge database, right? And its goal is to provide personalized answers to users, right? So, for example, if you ask the model, what did I do last summer, it will have all the information into your file system and it will give you an answer. Or it could provide recommendation for dining or for vacation, visiting, things like this, right? And this is really a black box scenario. We don't know what retriever model NVIDIA uses. They don't publish that information. For the generator, there are multiple options, and here we pick the default configuration. We did not play with it, so this is a Mistral model. So this is some example when the model, you just ask a question and it provides an answer. But then what we did, we wanted to attack this. And we wanted here to exfiltrate the context from the generator. And we considered here, we replaced the knowledge database with the Enron email dataset, right? This was our file system. And this is an example where we asked the question, what are some tips to improve my credit? And credit is the trigger, right? In this case, the attack is activated and we will poison the context. And now the model will output the top 4 emails, right, from the data set that were retrieved by the RAG system. So this, again, it's an exfiltration attack, and this is one of the emails. I don't have space to show all of them, but this is one of the emails in the context, and it shows someone's salary information. That's private information, right? So this is just an example, but of course, in a real system, we can extract probably credit card numbers or social security or, private information from users. We also did a denial of service attack that was easy to show as well. We can make the model refuse to answer, but I think the passage exfiltration is really more interesting. And we disclosed this vulnerability to NVIDIA, and they are currently investigating it. Okay, So we talked about privacy and security attacks on LLMs, on fine-tuning and RAG-based systems, and I'm pretty sure you are wondering how can we mitigate these attacks, what can we do to improve the security and privacy of LLMs. And unfortunately, I don't have very good news about mitigations, but I can briefly mention about some potential solutions and mostly open problems in this space to give you some ideas for what projects to work on. So first, let's start with privacy attacks. So to mitigate privacy attacks, the standard method adopted, in academia and industry is using differential privacy, training models with differential privacy, right? And this is a rigorous notion of privacy introduced almost 20 years ago, and we have methods such as DPSGD to train models with differential privacy. It's interesting to see that this has been adopted by industry. Google has released the Gboard, next word prediction model with differential privacy on multiple languages, and it achieves pretty good results in terms of utility and privacy trade-offs. But there are challenges. It's not like we have a tool and we are done, right? So differential privacy, by definition, it will mitigate both membership inference and data extraction attacks. But there are some challenges in that the theoretical privacy bounds are not very tight, right? And that means that privacy parameters are not set optimally, and this causes a reduction in utility. So a few years ago, we introduced this concept of privacy auditing, which is the idea of empirically measuring privacy leakage of an ML algorithm, right? And this will complement the theoretical upper bounds, so we can use privacy attacks to empirically compute lower bounds on privacy. And we can do this for different realistic threat models as well. And privacy auditing is a concept that has been actually adopted also by industry. For example, at Google, before they release a model in production, they do a privacy auditing, complete testing, right? And I'm sure at other companies as well. But the main issue with privacy auditing is that our initial method, as well as most of the literature, it's quite inefficient. They require training thousands and thousands of models in order to estimate these privacy bounds. And recently we made some progress on solving these issues in a recent paper published at iClear this year. We were able to do privacy auditing by training a single model, what we call one-shot privacy auditing. This is quite important for large models. As I mentioned, we cannot train additional models, right? So the idea here is to insert multiple randomized canaries, what we call canaries, like fake samples in the training set, and then perform some statistical tests on them to compute privacy bounds in one shot. But there are many open problems in the privacy space, like performing a detailed privacy analysis of generative systems like diffusion models, large language models, multimodal models, and so on, and consider these realistic deployment models, RAG, and fine-tuning. Then DP, also differential privacy, that does not yet scale to very large models like LLMs. Currently, they do not support training LLMs from scratch. There will be a huge computational cost and also a huge reduction in utility, so more work needs to be done there. And also scaling privacy auditing, making auditing also applicable to LLMs, and in general developing auditing methods both before and during model deployment. I think it's quite important. Now I want to mention briefly some open problems in AI security. We talked about these integrity violations in RAG-based system. I don't have a solution how to solve them. And I think we can try to use maybe some security principles, like using, for example, data provenance from the knowledge database, but it's quite challenging because the data can come from multiple sources. And potentially we could try to verify the LLM output using formal methods, or build certified defenses against poisoning. There is a recent paper that proposes this, but this induces an additional cost. And there is more work to be done to solve these issues. I want to mention that in my group, we are working on all these kind of open problems in trustworthy AI. We have 3 main areas, looking at adversarial machine learning, ML privacy, and using AI for cyber defense, and I'm happy to talk to you about any of these offline. Lastly, I want to mention this report that I co-authored together with NIST. It's a report on adversarial machine learning. It includes a taxonomy and terminology of attacks and mitigations. It was published earlier this year. I hope you find it helpful for your research. It has a chapter on generative AI. And we are in the process of updating it. We're planning to update this regularly as the literature develops more. And we will publish a new version soon, in a couple of months, to get additional feedback for next year. Finally, I would like to acknowledge all the funding agencies that support my research and thank all my students and collaborators. Without them, this work would not have been possible. And yeah, I'm happy to take questions. Thank you very much.
All right, thank you very much, Alina, for the presentation. We have a second microphone, so if you have a question. Weird, if you have a question, raise your hand. Yeah, okay. I'll give you this one, maybe it works.
First of all, thanks a lot for the great talk. The question that I have is about user inference. So you mentioned it is related to knowing whether this user participated in the fine-tuning phase. And I wonder what's special about the fine-tuning phase that makes this attack possible, and why isn't it also about the training phase? So, just like if a user participates in the training phase, can I also use this attack as well?
Sorry, I couldn't. Maybe you want to come closer because I couldn't. I couldn't understand. Yeah, the microphone is not great.
Okay. Thanks for the great talk. I'm just going to repeat everything. My question is about user inference attacks.
Yes.
So you mentioned it applies to users who participated in the fine-tuning phase. So what's so special about the fine-tuning phase that makes this attack possible? And does it also apply to the training phase? So not only
it could apply to the training phase as well. We did not test that because the issue is that for training these LLMs, we don't know which users the training samples belong to, right? Usually we don't have a label, like we collect data from the web, right, from Reddit or whatever website, but we don't know which user generated that post, so it's harder to test it. That's one reason. The other one is we would have to train ourselves an LLM, and we don't have the resources to do that from scratch, so it's really much easier to test this concept in fine-tuning, where you have these data sets that have annotations about users. So yeah, that's the reason. But the concept would apply to the training set. Yeah.
I see. And the thrust of the attack is that I don't know the exact data sample that was used by this user in this fine-tuning phase, but I know some other maybe relevant private information about the user, right?
Right.
But still, it's also a strong adversary model in the sense that it is not just like I know, for example, your name and your email address. No, I know private documents, and also I have the knowledge that these private documents are relevant or similar to the training data, right?
I see. Yeah.
Okay, so it is not just simply, I don't know, looking at the internet and grab data about you and just use them in that attack.
Right. You mean for the attacker? Yeah, the attacker does not need to know the exact training samples, right? So they might know they might see some post on social media, right, from a user, but they don't know which post from Reddit were included in the training set. But I can collect samples from the internet, or I can receive an email from this user and have some access to some samples generated by that user, but not exactly the training data, because that's hard. We don't have control over what data is included in training, right?
Okay, I see. Thank you so much.
Thank you.
I'm interested in your poisoning. Did you see that could be used for like marketing to seed results that people would see on a mass level, and we'll see a problem with that come future generations of AI?
Oh yeah, I didn't think about that, but yeah, as I mentioned, the framework is general in the adversarial objective, so you can come up with your own malicious adversarial objective. We can write it as an optimization problem and we can solve it. So yeah, it can be used for much more than saying, sorry, I don't know, right? Which is kind of the easy thing to test on. But yeah, there would be like, yeah, it could generate content, like you say, marketing about particular company, right? Things like this, yeah, for sure. So we need a solution, right, before we deploy these models in the real world.
Thanks.
Thank you.
Yes. Hi, Alina. Thank you for all the great work and the great talk.
Thank you, David. Yeah.
I'm curious, what are some of the biggest challenges and how do you mitigate those challenges in terms of conducting this type of research, getting access to the data, the models, and all the other resources that you need?
Yeah, great question. So yeah, it turns out that there are lots of models that are publicly available by Hugging Face. This GPT Neo, for example, models, Llama, all these things are available. The main, and data sets are also public. What we used here, these data sets were all public. They are available. The main challenge is computational resources, honestly, like even performing fine-tuning. We did our experiments on a very small model, 128 million parameters, because fine-tuning a 7 billion model, we don't have the computational resources ourselves. Of course, in industry, that's not an issue. Like companies would have huge clusters, but for academic researchers, I think computational resources, it's a big challenge.
I'm also curious how you managed to get such a wonderful set of partners to support your work.
Yeah, well, yeah. It's a lot of work, but yeah, I was fortunate also to have access to collaborate with a lot of people and get a lot of proposals funded. I wrote a lot of proposals. Most of them are declined, but you know, some are funded. Yeah.
Thank you.
Thank you.
We have time for one more question.
Hi, thank you again for the talk. So you mentioned at the end about being able to audit the models to check properties of the models that are being produced. Is this mainly for the model generators, or are there ways that the properties can be publicly verified by other people using the models?
Oh, you're talking about what I discussed about open problems.
Yeah.
Yeah, I was thinking more about, in particular, about this integrity attack that I showed, right? That you ask a particular question and clearly the answer is not even related to the question, right? So you can potentially verify that the output at least matches, or you can use other sources and check that this is valid. But in some cases, it's very subtle to determine that this is real, like the marketing. I think the what you had, right? This is very subtle, right? To determine that there is an attack there or not. Yeah.
Thank you very much.
Thank you.
All right, thank you very much, Alina.